We are now live on YouTube. Hello, YouTube.
And we're live here too.
Yeah, in the chat.
Yes.
Cliff, hi. Soon people are going to say hi from Blair, and we'll try to keep up, but we won't be able to. But it's good to see everyone. Yeah. Chat. Cliff, hi. Soon people are going to say hi from Blair, and we'll try to keep up.
We hear your
Everyone.
10-second delay, Dave.
There we go. Thank you.
Yeah, no worries.
I have two streaming windows open, and one of them was not auto muted. There we go. Thank you.
We still hear it. Neither one of them are auto muted, maybe?
We still hear it.
Is it me?
It's not for me, so
Testing 1 2, testing 1 2.
me, so well,
Testing 1 2, testing 1 2.
Let's just do it. I think it's okay.
Do y'all not hear
thanks
the
for the-
echo? Is it just me?
I don't know, a disconcerting echo.
Do y'all not hear the echo? Is it just me?
I'll be muted for like the entire time after this, so hopefully no echo if it's me.
Disconcerting echo.
I am definitely hearing the echo.
Oh, new technology. Oh, Christopher says he doesn't hear the echo. How about anyone else out there before we get this really started? Do you hear a few rounds of us? Brian, it might be you. I don't hear it now. Okay. Thank you for everyone chiming in the chat. All right, Brian, you are muted, so I
It's
don't hear
still
any
there.
echo. Oh, maybe you can.
All right, Brian, you are muted, so I don't hear any echo. Oh, maybe you can.
I'm hearing all of you and your mouths aren't moving.
This is new and interesting. Okay, give us just 1 second. We're going to get this technical difficulty started. Casey, I wonder if you could talk and we'll all mute and make sure it doesn't happen when that goes on, because that's the important part.
Okay, how about now? Any echo? Nope. Okay, cool.
Okay, so forgive us if there's an echo just for the intros, and then as soon as Dr. Honniball gets started, we will stop that. Brian, take it away.
Take it away.
I don't know, I heard that twice. Well,
Let's just roll with it.
Okay, so let's make believe that this is gonna work. Maybe. Just roll with it. Let's make believe that this is gonna. Just roll with it. Three of them now.
Brian, I don't think it's getting
Tear
any
off
better.
the Band-Aid. Let's go.
Yeah, let's do it. Just listen to the loudest echo and let's see if we can get through there.
Brian, I don't think it's getting
Tear
any
off the
better.
Band-Aid. Let's go.
Yeah, let's do it.
Okay, so welcome. Okay, welcome. Hello, everyone. Welcome to the May NASA Night Sky Network member webinar. Welcome. Welcome. Hello, everyone. Welcome to the May NASA Night Sky Network member webinar. Oddly enough, it was me. Who would have
Let's
thought?
start over. Okay. Wonderful.
So I went and looked, and it's kind of like that. I tried to edit the thing the other day, and apparently it decided that I was going to be there live. So apparently it was open, hidden in the depth. Oh. Okay. I should have known. Okay. Sorry, everyone. We gradually sorted it out. So restarting. Hello, everyone. Welcome to the May NASA Night Sky Network member webinar. We're hosting tonight's webinar from the Astronomical Society of the Pacific in San Francisco, California. We're very excited to present this webinar with our guest speaker, Dr. Casey Honniball from NASA Goddard Space Flight Center. Welcome to everyone on YouTube and everyone on Zoom. We're very happy that you're all here. These are monthly events for members of the NASA Night Sky Network, and we're also streaming them for the world on YouTube. For more information about the NASA Night Sky Network and the Astronomical Society of the Pacific, please check the links in the chat where hopefully you can find it. Well, that's not even working for me. There we go. So before we introduce Casey, here's Dave Prosper, who may or may not have an announcement.
Hi. It's actually fairly quiet today on the Night Sky Network. So we don't have really any announcements today. Just be safe when you're going out. Enjoy the stars. It's getting nice and warm out. And hope you all have great stargazing. There is an eclipse, I believe, very soon, next week on the morning of the 26th, if my memory serves right. So hopefully you can all get a good view of that, especially West Coast and beyond. That's really it. Vivian, I don't know if you got anything. Nothing. Okay, there we go. All good. Easy. Back to you, Brian.
Okay, for those of you on Zoom, you can find the chat window and the Q&A window at the bottom edge of the Zoom window on your desktop. Please feel free to greet each other in the chat window or to let us know if you're having any technical difficulties. You can also send us an email at nightskyinfo@astrosociety.org. If you have a question for Dr. Honniball, please enter that into the Q&A window. Keep your chatting with each other in the chat and all the questions into the Q&A. That will definitely help us keep track of your questions and let us know whether or not we've answered them or not. So again, welcome to the May webinar of the NASA Night Sky Network. This month, we welcome Dr. Casey Honniball to our webinar. Dr. Honniball is a lunatic, a lunar scientist, research fellow in the NASA Postdoctoral Program at NASA's Goddard Space Flight Center. Her current research focuses on characterizing water on the moon and testing field portable instruments for use by astronauts during their EVAs on planetary surfaces. Her PhD is in Earth and Planetary Science from the University of Hawaii, and she and her team announced the direct detection of water molecules on a sunlit portion of the moon using the air-borne telescope SOFIA. Since then, she's made numerous media and outreach appearances to talk about lunar water, including joining us here. So please welcome Dr. Casey Honniball.
Hi, everybody. All right, let me get my screen sharing. Okay, let me know if this is not sharing for you guys.
Looks good for me.
All right, so hi, everybody. Thank you so much for allowing me to talk to you today. So as he said, my name is Casey Honniball, and I'm a NASA postdoctoral fellow at NASA Goddard Space Flight Center in Greenbelt, Maryland. Today, I would like to talk to you about the NASA Artemis program to explore the moon like never before, and how we're preparing for a sustainable lunar presence using the moon's most important resource, water. So Artemis is the twin sister of Apollo and goddess of the moon in Greek mythology. Through the NASA Artemis program, NASA is preparing to land the first woman and the first person of color on the moon using innovative technologies to explore the moon and the lunar surface more than ever before. We will work with academic, commercial, and international partners to establish sustainable presence on the lunar surface. And we will use what we learn on the moon to explore even farther and take the next giant leap of sending astronauts to Mars. To embark on the goals of Artemis. Everything okay?
Looks great.
We're good. We're good.
Okay. So to embark on the goals of Artemis, we need a system to get our astronauts to the moon. They will launch on the world's most powerful rocket, the Space Launch System. They'll ride in the Orion capsule to the lunar outpost called the Gateway that will be in orbit around the moon. From the Gateway, astronauts will descend to the lunar surface via the recently selected SpaceX Human Landing System. Through this system, we will have access to all locations around the moon. America will be again a leader in space exploration. The Artemis program will advance us from mapping the moon to establishing a sustainable presence on the lunar surface. From studying the moon from samples and instruments to exploring the surface in person. And from learning about Mars to answering fundamental questions about the history of water on both the moon and on the Martian planet. So the Artemis mission is made up of two phases. Phase 1 is to achieve human landing on the surface of the moon, and phase 2 is to build a sustainable presence on the surface of the moon. So I'll focus on phase 1 here, and that's the current mission phase. So during this phase, we are preparing to send our astronauts back to the moon. We will first send Artemis 1 into orbit around the moon to return safely home. This is an uncrewed integrated flight test of NASA's Orion spacecraft and the Space Launch System. This mission will last anywhere between 26 to 42 days and is expected to launch in November of this year. Artemis 2 will be the first crewed mission of 4 astronauts with the objective of confirming all spacecraft systems operate as designed with crew aboard and in the actual environment of deep space. During all of this, the Gateway lunar outpost will be assembled. First, the solar electronic propulsion system will be sent to orbit the moon. And then the first pressurized module will be installed. And then lastly, the human landing system will be delivered to the Gateway to prepare for Artemis 3. Artemis 3 is the main headliner. It will send 4 astronauts aboard the Orion spacecraft and head to the Gateway outpost. Once there, 2 astronauts will stay aboard the Gateway, while the other 2 head down to the lunar surface on the human landing system. Once on the surface, the astronauts will spend a week on the surface conducting science experiments and setting up infrastructure that will begin the next phase of building a sustainable presence on the surface of the moon. So many people have said, we've been to the moon, why should we go back? Or why not go straight for Mars? The answer to this is actually very simple. The moon is our closest celestial neighbor, and it is just a 3-day trip away, compared to the 8 months it takes to get to Mars. By going to the moon, we can develop new methods that we need to survive on Mars while being within reach if something were to go wrong. On Mars, if something goes wrong, you're on your own. It's better to test our habitats, technologies, and procedures on the moon before sending astronauts to Mars. With the ultimate goal of expanding humanity's reach into the solar system, the moon is a critical stop for turning science fiction into reality. While on the moon, we can test new technologies for life support systems or construction of habitats in low-gravity environments and extreme conditions. All of the work we do on the moon prepares us to make the journey to Mars. The return of American astronauts to the moon will place America in a leadership role for space exploration similar to the Apollo era. It will inspire the next generation and encourage careers in science, technology, engineering, and mathematics. The Artemis program will feed back into our daily lives, just like Apollo did, with new technology being developed and adapted for our everyday use in our everyday lives. To fulfill humanity's basic desire to explore, the moon is the next frontier. So let's go over a little bit what we've learned about the moon and what we currently know. So prior to Apollo missions, little was actually known about the moon. Here are just a few things that Apollo taught us. Originally, we thought the moon was only hundreds of million years old. But once Apollo returned samples, we learned that the moon is actually 4.5 billion years old. This is similar in age to the Earth. We expected the moon to be made of unmelted, primitive meteoritic material that formed by accretion and has always been cold. But what we found from Apollo samples is that the moon is actually made up of rocks that can only form inside of magma. The theory that all planets form cold was dismissed, and the moon had to be molten when it formed. And long ago, early astronomers believed that the dark patches on the moon, known as maria, were once dried up oceans. However, most lunar geologists actually knew that the maria were lava beds, but they expected the moon to be very dry, but they weren't sure how dry. Well, it turns out that the moon isn't entirely dry, and water can exist on the surface. And the maria were never oceans of water, but they were actually oceans of lava. So now I'm going to play a video for you about the evolution of the moon, and it's going to give you a glimpse of how the moon formed to what we see today.
From year to year, the moon never seems to change. Craters and other formations appear to be permanent now, but the moon didn't always look like this. Thanks to NASA's Lunar Reconnaissance Orbiter, we now have a better look at some of the moon's history. The moon likely started its life as a giant ball of magma formed from the remains of an impact on Earth about 4.5 billion years ago. After the hot material collected into a sphere, the magma began to cool, eventually forming a crust on the surface of the moon with the magma just underneath. Around 4.3 billion years ago, a giant impact battered the moon's south pole, forming the South Pole Aitken Basin and sending debris as far as the opposite side of the moon. This impact marked the beginning of a period that would cause large-scale changes to the moon's surface. One by one, more huge collisions shaped the terrain, some forming large basins that would eventually fill in to become the dark-colored patches of the moon, known as maria. They began as normal craters, but soon started to change due to the size of the impact on the relatively thin crust. Because the moon had not yet fully cooled on the inside, lava began to seep out through the cracks caused by the impacts. The resulting volcanic activity spread lava throughout the craters, gradually filling them in and cooling. Because of the high iron content of the basalt in the rock, the maria reflect less light and therefore appear darker than the surrounding highlands of the moon. Around 1 billion years ago, volcanic activity ended on the near side of the moon as the last of the large impacts made their mark on the surface. The moon continued to be battered by other impactors, although they were much smaller than the objects that formed the largest basins. Some of the largest, most recent, and best-known impacts from this period include the Tycho, Copernicus, and Aristarchus craters, which are unique due to the complex system of rays that stretch out from the impact site. Finally, we arrive at the moon that we see today. Though the surface continues to be affected by impacts, the rate has slowed down drastically to the point where the moon appears unchanging to the human eye, as a permanent record of its own history, and a glimpse of how craters may have formed here on Earth.
Okay, so let's continue this little tour of the moon. We always see the near side of the moon, and that's because the spin of the moon is the same length and time that it takes the moon to orbit the Earth. The near side has two distinct features, the light areas of the highland and the dark areas of the mare. These two features represent rocks of different composition and age. They provide evidence into how the early crust of the moon formed from the giant ball of magma. Craters that formed expose material from deep inside the moon and preserve the impact history of the moon and other bodies like the Earth where the impact history has been erased. The far side of the moon, however, many people have never even seen an image of. You might think it should look the same as the near side. But instead what we see is that the far side of the moon looks nothing like the near side, with only 1% of the far side being covered in the dark mare patches. The near side has higher concentration of radioactive elements that decay and produce heat inside the moon, making it easier to produce magma that can erupt into from lava flows. The near side also has a thinner crust from many large impacts, also making volcanic eruptions easier. On the far side, there are not many large impact basins, and the crust is a lot thicker, making the volcanic eruptions a lot harder on the far side, and so the appearance of the dark mare patches is rare. So even though we've been studying the moon extensively for decades now, there's still many things we don't know about the moon. So what can we still learn about the moon? So I'm going to play one more video for you, and this one is actually my favorite. it's going to walk through just a handful of things that we still need to learn about the moon.
The moon is our nearest neighbor, our nightlight. It's also our memory. While wind, water, and molten rock erase Earth's deep history, the moon remembers everything that has happened in the last 4.5 billion years. The impact that formed the Oriental Basin provides a window to understanding how similar large events on other planets and moons have shaped their landscapes. The discovery of water on the sunlit surface of Clavius crater not only unlocks new possibilities for future lunar exploration, but also our understanding of where the ingredients of life could exist in our vast universe. The steep trenches and cracked surface of Komarov crater on the far side tell a story of the ancient volcanic activity from the moon's interior, revealing the history of geologic forces carving the lunar terrain through time. Traversing the landscape, we can see a beautiful tapestry of ridges, valleys, and mountains, best encapsulated by the view of Tycho crater. The summit of its central peak stands nearly 3 miles above the crater floor, a visual metaphor for the steep challenges but exciting rewards that await us on the moon and beyond. And on the lunar horizon, the most consequential view of all, our home. To study the moon is to study ourselves, our past, our present, and our future. Each new discovery bringing us from darkness into light. The gravitational forces between Earth and Moon make our very existence possible, creating one of the most special relationships throughout time and space.
So this video only touches on a handful of things that we can still learn about the moon, but there is so much more we still don't know. By returning to the moon, we can learn more about planetary processes, like how volcanism shaped the moon we see today. We can find the origin of polar volatiles like water ice, study the history of impacts on the moon that tells us about Earth's bombardment history, which has largely been erased by weathering, erosion, and plate tectonics. We can look at the behavior of the sun over the past 4.5 billion years ago. We can set up a radio telescope on the far side of the moon, away from all the noise that confused radio signals here on Earth. We can test how physical and biological systems behave in low gravity and vacuum environments. And lastly, we can study the risks of space exploration and work to mitigate them for safer exploration to planets like Mars. Another unique thing about the moon is that it provides access to resources. The image in the back is a geologic map of the moon's near and far side. The colors represent different minerals. All of the minerals can be extracted for resources. The list in the middle are just some of the resources the moon has to offer. These can be used for a variety of purposes, such as life support, building materials, fuel, or power. The Artemis mission relies on research we do to understand the processes occurring on the moon and the available resources. So the moon is a cornerstone for solar system science. For the Artemis program to be successful and sustainable, we need to understand everything the moon has to offer. Of particular interest are volatiles on the moon, such as water, which is likely going to be the moon's most important resource. But before we can prepare to use any water on the moon, we must first understand its life cycle, sources, deposits, and losses. So why is water so important? For humans to survive anywhere, we need water to drink. But water can also be broken down to create breathable oxygen, rocket fuel. If we find that the moon has large enough quantities of water that we can use, then when we send astronauts to the moon, they won't need to bring all the water and fuel they need for their stay. Take camping, for example. If you go backpacking in a dry, remote location, you need to bring everything you need to survive. Imagine having to carry 3 gallons of water for a 5-day camping trip. That would be pretty heavy during your journey to the camping site. Now imagine instead that you're camping next to a river. Instead of bringing all the water you need, you just need the correct materials and supplies to make the river water safe to drink. This would be much less weight to carry. For space exploration, launching water is expensive, costing roughly $25,000 per gallon of water. So if we can use water from the moon, we can create a more economical and sustainable presence on the surface and journey farther out into the space. So, what do we know about water on the moon? Let's go back in time to 1952, 17 years before Apollo 11 would land on the moon. It was theorized that the poles of the moon, inside regions of permanent shadow, there would be water in the form of ice. This video here is zooming in on the south pole of the moon, showing where sunlight shines. If you pay close attention, you'll see some areas never receive any sunlight. These are the permanently shadowed regions that were theorized to store water ice. Now, let's watch this video one more time. So this time you're going to notice that when we zoom in to the South Pole, you're going to notice there's these blue areas, and these are all of the permanently shadowed regions. You might notice there's a lot more of these regions than you saw in the first video. So it's these areas in blue that scientists in 1952 thought might be trapping and storing water ice. However, once Apollo missions returned samples from the moon, researchers found no evidence of water of any kind or form. This led everybody to believe that the moon is a very dry place. But as the years passed, new and improved technology emerged. In 2008, researchers decided to reanalyze special Apollo samples. During Apollo 15 and 17, some samples that were brought back contained black, green, and orange glass beads. This image shows an Apollo 17 sampling site where you can sort of see that the regolith here appears to be orange. Now, taking a closer look at this, the orange soil really stands out against the gray regolith or soil of the moon. The glass beads that were found during Apollo 17 were orange and black. And these beads are special because they formed during a volcanic eruption on the moon. These beads were reanalyzed with the new technology, and researchers found high water contents inside the beads. Now, what they actually measured was hydrogen, but the amount of hydrogen measured can be converted to the amount of water present if all of that hydrogen was in the form of water. The next year, in 2009, 3 spacecraft reported the detection of a hydration feature on the surface of the moon, something that no one actually expected. These images here were taken by the Deep Impact spacecraft that did a flyby of the moon. This last image here on the right shows how much hydration Deep Impact measured, with the reds and yellows representing high amounts of hydration. The 3 spacecraft all detected what we refer to as the 3-micron hydration band. 3 microns is an infrared wavelength just beyond what our eyes can see. This plot on the left is showing an example of this 3-micron hydration band similar to what the spacecraft would have observed. This band is created by molecules that have both a hydrogen and an oxygen atom present. This means that the 3-micron hydration band is attributed to the presence of either hydroxyl, which is OH, water, H2O, or both. So for example, if drain cleaner's active ingredient is hydroxyl, and if water and drain cleaner were on the moon, we couldn't distinguish between the two at 3 microns. In the same month that the 3-micron hydration band was reported, a man-made projectile struck a permanently shadowed region inside Cabeus crater located at the lunar South Pole. The goal of this L-Cross mission was to eject debris, dust, and vapor, which may contain highly volatile substances like hydrogen gas, ammonia, methane, and water. By observing the ejecta, L-Cross detected water vapor and water ice. This detection is the first evidence of water on the moon in permanently shadowed regions, like had been predicted in 1952. Following the L-Cross mission, water on the moon was mainly studied using data obtained from the moon mineralogy mapper on board the Chandrayaan-1 spacecraft that collected global observations of the moon in the near-infrared, including that 3-micron hydration band. This map shows high hydration in blue, mainly at high lunar latitudes near the poles. Using the same data set, in 2018, MCube researchers were able to make a map of water ice at the lunar poles. This image is of the South Pole, and water ice is found at all of those locations in teal. All the water ice detected by MCube resides within these permanently shadowed regions. Now, up until last year, all evidence for the actual water molecule on the surface of the moon was in the form of water ice in these permanently shadowed regions. But outside these cold, dark places, water on the sunlit moon had never been detected. And scientists were still trying to figure out if this 3-micron hydration band was even partly due to water. So let's go over why there's such confusion about the 3-micron hydration band. The 3-micron signature of hydration is created when a hydrogen and an oxygen atom are bound together. The molecules containing hydrogen and oxygen stretch symmetrically and asymmetrically, like shown by these little molecules here. This motion of the molecule shows up as the 3-micron hydration band, like shown in this plot. The 3-micron signature for hydroxyl is similar to the 3-micron signature of water. Further complicating things is that hydroxyl binds to lunar material, allowing it to mimic water's signature almost exactly. As of right now, we don't know how to separate the two at 3 microns. So with the 3-micron band on the sunlit moon, it could be either hydroxyl or water. This is where part of my work on lunar water comes in. Previously, all the detections of water and hydration was done in the near-infrared, where water and hydroxyl can be confused. This got me and my graduate advisor wondering why we're not looking for a different water-only signature to determine if water can survive outside of these permanently shadowed regions, but on the sunlit surface of the moon. So we developed a new method to look for water on the moon, simply by looking at a different part of the electromagnetic spectrum. So we shifted from 3 microns to 6 microns, which is a little bit further into the infrared. And at 6 microns, the water molecule has a unique signature due to the bending of 2 hydrogen atoms around an oxygen atom, like this little water molecule here is doing. Hydroxyl doesn't move like this, and so does not confuse the 6 micron signature of water. To search for water on the sunlit surface of the moon, at 6 microns, I use the Stratospheric Observatory for Infrared Astronomy, SOFIA. SOFIA is unique because it's a telescope on an air-borne Boeing 747 flying at 45,000 feet. This is an illustration of what SOFIA looks like while it's flying. You can see that there's a cutout in the side of the plane that opens up to reveal the telescope. So with SOFIA, we looked at the Clavius, let me go back. So with SOFIA, we looked at the Clavius crater at high southern latitudes, indicated by the white circle on the moon. With SOFIA, we were able to detect the water signature at 6 microns, making it the first time that water itself was detected on a sunlit surface of the moon. This answered the decade-long question of, can water survive outside of these permanently shadowed regions? This image on the bottom is an oblique view of the Clavius crater where we found the water. The amount of water that we found, however, is quite low compared to Earth standards. For comparison, the Sahara Desert contains 100 times more water than what we detected at the Clavius crater. So we won't be going swimming on the moon anytime soon. So now you may be wondering, well, how did all this hydrogen and water get to the moon in the first place? Well, there's a few ways. One way is when the moon was first formed and before it formed a solid surface, comets carrying water impacted the moon and left behind water inside the lunar interior. This internal water would later be erupted onto the surface of the moon through volcanic events or dredged up during a large impact that created some of the craters we see today. Another way is that solar wind that constantly bombards the moon. The solar wind is a stream of charged particles released from the sun and is mainly made up of hydrogen. When this hydrogen hits the moon, it reacts with oxygen and lunar materials lunar minerals and forms hydroxyl and possibly water. And another major way water can get to the moon is through recent micrometeorite impacts. Micrometeorites, like comets, can carry water to the moon or produce the water from during an impact. So now we have the history of lunar water, and we know how it got to the moon. So the next questions are, where is the water? How is it stored? And how can we extract it and use it to support astronauts and human exploration? Well, we already know that water is trapped inside these permanently shadowed regions at the lunar poles that are super cold because they never receive any sunlight. At places like this, water is trapped as frost, like you might see on your grass on a cold winter morning, or it could be on little grains of ice mixed into the lunar soil, or it could be a large deposit like an ice sheet. Water ice within these cold, dark places at the lunar poles could be in abundances of tens to hundreds of million tons. But however much water ice is there, the ice is not pure, and so it would need to be refined after being extracted. To extract ice from these permanently shadowed regions, it requires a lot of preparation. The first challenge to extracting water from these regions is the fact that these places are really cold and dark. For example, these regions typically sit around a temperature of negative 390 degrees Fahrenheit. The coldest place on Earth is in Antarctica, but there it only gets down to negative 130 degrees Fahrenheit. Power is another big issue. For space exploration, power is typically generated from solar panels. But when working inside a permanently shadowed region, there's no light available for the solar panels. Batteries are not very useful in extremely cold temperatures and would need to be rechargeable. So to power all the instruments and life support systems for astronauts, we need a reliable power source. Some ideas for this are to have solar panels on towers that can extend high enough to reach the sunlight. Nuclear power is another one, or regenerative fuel cells. Once we get the power inside these regions, we next need to figure out how to extract the ice. There are a couple companies and groups looking into how to extract water ice from permanently shadowed regions. Here I'm only going to talk about 3 potential ways. One way is to heat the lunar soil containing the ice. In this method, the lunar soil is heated to temperatures that are high enough to vaporize the ice. The water vapor is then collected, refrozen, and transported out of these permanently shadowed regions. This method, however, requires a lot of power to heat the lunar soil. Another way is to excavate a large amount of lunar soil and transport it out of the permanently shadowed region to be processed. This is not very efficient, though, as you are hauling out thousands of tons of lunar soil that is not wanted just to extract the ice. And the third potential way is to sort the ice grains from the lunar soils. This method would be similar to how gold miners separate gold from other materials. The ice grains in these regions are as hard as granite, and therefore they can be separated from other grains. This method does not require changing the water ice to a vapor phase and back to ice, and it doesn't require hauling out tons of excess materials. Once the ice is extracted, though, it is taken to a chemical processor that vaporizes the ice, purifies it, and then it can either be converted to oxygen, rocket fuel, or water for the astronauts. So since we did find that water can survive on the sunlit portion of the moon, we may be able to extract water from a less complicated location. The water we detected with SOFIA at the Clavius crater could either be attached to lunar grains or stored within impact glasses. Extraction of water from these 2 water locations requires heating the lunar soils or glasses. If the water is just attached to a lunar grain, then we only need to heat the soil enough to break the bond and capture the water. If, however, the water is stored inside these impact glasses, extraction requires high enough temperatures to melt the glass and release the water. Extraction of this water is less complicated than that of water ice in the permanently shadowed regions. There is a catch, though. The amount of water from the water attached to lunar grains or stored within impact glasses is much, much smaller than the amount of water ice in permanently shadowed regions. So this method may not yield a lot of water and therefore may not be feasible. There are some locations, however, outside of these permanently shadowed regions that could potentially concentrate water. These are the volcanic deposits that contain the glass beads. The beads may store water from the lunar interior and could be melted to extract water if the abundances are high enough. Another possible route that doesn't include mining water, but instead producing water from the moon and the lunar soil. Most of the lunar soil is made up of minerals that contain oxygen. One mineral of particular interest is ilmenite, which is made up of iron, titanium, and oxygen. Experiments using ilmenite in Apollo samples have shown that water can be produced by heating the sample and adding in hydrogen. So basically what happens to the sample when it is heated and hydrogen is added, the ilmenite breaks up into free iron, titanium dioxide, and most importantly, water. But a byproduct of this reduction of ilmenite is the release of iron. Iron is also a resource on the moon that could be used for building materials. This process, while promising, has only been done on a small scale, but the European Space Agency is already planning to test this on the lunar surface with the Roscosmos lander in 2023. One of my colleagues, Hannah Sargent from the UK, is actually working on this. So in order for this process to work though, there needs to be a lot of ilmenite. And the best place for that is on the mare, which are the dark patches we see on the moon. Now let's come back to Artemis and how we are preparing to send humans back to the moon. I already talked a little bit about the work I do with SOFIA, but how does my work on lunar water help us prepare for the Artemis program? Basically, I am an observational lunar scientist. I use 2 Earth-based telescopes, the Stratospheric Observatory for Infrared Astronomy, SOFIA, and the NASA Infrared Telescope, IRTF, in Hawaii. With these 2 telescopes, I am trying to understand and characterize the behavior of water, its abundance, and its distribution across the moon. By understanding how water may be moving around the surface of the moon, we can determine the source of water and the retention of it. By looking at the distribution of water across the moon, we can estimate its abundances. We can look for places that could be concentrating water, that could be potential landing sites for Artemis in the future. So this is a very exciting time for lunar science and exploration. The moon is a spectacular sight and something that all humans on Earth have in common. Thank you all so much for allowing me to talk today. I hope you enjoyed learning about water on the moon and the Artemis program.
All right, well, thank you so much. This is really great. There were some really interesting things that I had never heard before, and so that's fantastic. And we have some really great questions here too. And so let's get right to these. So a while ago, Darian asked, what is the geothermal gradient on the moon? Is it similar to Earth's 30 degrees C per kilometer? Can the heat from the interior be used for electricity? Any kind of geothermal energy generation, either there or on Mars, if you want to think about a comparison between the two.
Yeah, that's actually a really interesting question. I am not a geothermal person, but I can take a stab at this question. The moon is pretty cold now and likely doesn't have any active heat sources, maybe at the very, very core, but we don't know. So any type of geothermal activity would be hard to tap into on the moon. For Mars, that might be different. I don't study Mars very much, so I'm not really sure. But Mars is a lot colder than the Earth is. So I think that the geothermal activity would be a difficult thing.
Although it's interesting, just a couple of days ago, it seems like I read that they think that they have found evidence of perhaps some current activity on volcanic activity on Mars, but I think it's an open question. So
that would be definitely very interesting.
It would. One of the things that Brian Day, I'm sure you know Brian Day, who does the Mars Trek and the Moon Trek visualization tools. And one of his favorite things to show off are the volcanoes on the moon. And I said, well, current volcanoes, well, here they are. So, what's the evidence? So, okay, William asks, the South Pole craters are deep with steep sides. If water or ice is in these craters, how can you access it?
That's a good question too. That is part of what we are exploring now, trying to figure out how do we get into these permanently shadowed regions? How do we survive in them? Some of the ideas for getting into craters with steep walls, or even the volcanic vents that are found on the moon, is to have a two-wheeled little rover that's tethered to the main rover, and to let it kind of send it out over these crater walls or down into these volcanic sky vents. So it would basically be tethered, and the tether would help control its descent. That is one possibility for getting into these areas.
All right, so let's see. Stuart asks, how is the crystalline water extracted if sublimation may cause loss while extraction, during the extraction process?
Yeah, so in the permanently shadowed region, what they would do is, if they're going to heat the surface to extract the water and make it a vapor, they would put a cap over the area that they are heating. I've seen illustrations of this where there's an entire crater floor covered by this big sheet, and underneath it, it's being heated, and the water vapor is then collected underneath the sheet. And that's how they're explaining that.
Okay, so Jamie asks, since this is a new engineering challenge of how to get the water out. So Jamie asks, is water extraction potentially planned for an Artemis mission, maybe later on, Artemis 5, 6, something like that?
I believe that Artemis is definitely going to be testing water extraction experiments. I don't know of any that are currently planned, however.
Okay, so let's see, we have Al asked a question. Could mirrors in, I guess it's not geosynchronous, but lunar synchronous orbit shine sunlight on the shaded areas to melt the ice?
Yeah, that's actually been an idea that's been proposed. Instead of having it in orbit around the moon, I've seen illustrations of where it's like this big giant tower with a mirror shining the sunlight down into the crater. That is something that scientists are thinking about.
Well, if anything's crazy enough to think about, somebody's probably thought of it. So it'll be interesting. Probably the way that they'll end up doing it is going to be so innovative that no one is even thinking about it now. So William asked a question: would you need a water refinery on the moon similar to an oil refinery on Earth?
You would definitely need to refine the water, because it is not going to be pure. It is going to be mixed with all the lunar dust, and if you've seen pictures of Apollo astronauts, they're covered in this stuff. So it would definitely need to be purified.
Okay, so a different William, we have several Williams, is the Department of Energy working on nuclear designs for powering space settlements? Or is that something, under development with someone else?
I would assume that they are under development, but that is definitely not my area of expertise.
Okay, so Mary asks, are there North Pole craters that are permanently shadowed? And if so, could they also contain water?
Yes, so we have actually made a map of the North Pole water ice deposits as well. They are correlated to the permanently shadowed regions. However, the North Pole doesn't have as many large craters that are permanently shadowed, and the water ice deposits are a little bit more patchy at the north. So we are focusing on the south because they have higher chance of having these large water ice deposits than the north does.
All right, we have still another William, a different William than the previous ones. So William asks, lava tubes are sunless with low elevation. Any search for evidence of hydration near these tubes or missions to explore near them?
Yeah, so this is part of that little two-wheeled rover attached to a tether. That's what they want to do. They want to go inside these areas and see what's in there. Is there a concentration of volatiles in there? Because they are a permanently shadowed region at a lower latitude where you could potentially extract some resources. We have no data on what's actually inside them yet. We do have a little bit about the stratigraphy of the crater or of the skylight walls, but down inside, we know the temperatures are low enough to possibly support it, but we've never been in there, so we don't actually know what's going to be trapped in there.
So many mysteries. We just have to go.
Exactly.
Okay, so Stephen asks, would the Earth's gravity create microtides of any hidden water on the moon?
That's an interesting question. I'm not sure about microtides, but we do know that the Earth's atmosphere does extend out to the moon. So there is a potential for some of the Earth water to be deposited onto the moon. Of course, that's a very, very small amount.
Okay, so Don asks, so once you are able to extract the water, what are the plans for containing and storing the water once extracted?
Ooh, I don't know. I assume that they would have large tanks where they could cool the water enough so that it's in liquid form, which is the smallest volume that it could take up, so that it could be stored. They could store liquid hydrogen, liquid oxygen for rocket fuel. They could store the liquid water. I'm sure it's something people are thinking about, but I don't know.
And I guess that's one of the things. There are different branches at NASA. So, you know, I'm guessing you're in the Science Mission Directorate, perhaps, or maybe you're in Human Exploration, but there's probably different, areas that are thinking about these engineering challenges. So a different Stephen, we have a lot of, questions coming from people with similar names. So Stephen asks, why was your team the first to look for the 6-micron feature, especially since there had been interest in water for so long?
I ask myself this question every single day. I have no idea why people didn't look before. In 2001, it was actually suggested that the 6-micron region could prove the existence of water on the sunlit surface of the moon, and nobody did it. So it beats me, but they didn't do it, so I got to do it.
Well, that's a good thing.
Yeah, a good thing for me.
So was that the subject of your dissertation, your doctoral research?
It made up one chapter of my PhD. The other chapter was on characterizing water on the surface using the IRTF telescope and the 3-micron hydration band. And then also another chapter was on building an instrument to look at volcanic gases here on Earth.
Okay. And so how, just kind of curious, how does that translate into thinking about what's going on the moon, or was it just purely a terrestrial effort that part was?
So the instrument that I was building was actually a field portable hyperspectral imager that looked at volatiles. And our idea was, if you can make an instrument small enough in this really interesting 3-micron to 6-micron wavelength range, and you could put it onto smaller satellites to go in orbit around the Earth for fire detection or methane gas leaks and hazard management, or you could put it into orbit around the moon to look for like carbon dioxide or water.
Okay. Yet another example of NASA technology being applicable to challenges here on Earth. So it's spin-offs. So technology spin-offs, I guess. Susan asked a question. You alluded to this, that the moon in some ways is a record of the ancient sun. And so how does that work?
So basically, the solar wind has been implanting hydrogen and helium into the surface of the moon for billions of years. And so what we can do is we can take the rocks from the moon and study the isotopes and study how the sun might have changed over time. And
so you can do that remotely, or is that something that you actually have to do on site when people?
Yeah, you definitely need the samples. You need to collect samples and take them back to your lab so that you can do all the analysis on the isotopes and different elements that are present.
Okay.
And also different layers too.
Okay. So Stuart asks, has iron oxide been detected on the moon?
So there's actually this theory that the moon is rusting. So there is the idea, or there has been observations of iron on the moon.
So let's see, Patrick asks, are there any lava tube type structures that might be integrated into a base structure? And so what sort of thinking is going into potentially utilizing those?
Yeah, the volcanic skylights are definitely a place of potential shelter. It's a natural formation that if it has a structural tube that is safe for us to enter and stay in, then it could be a natural shield from the harsh radiation environment of the moon and the sun. That is definitely something that is being explored. My only question is, how do you safely get in and out of a lava tube skylight? Because these aren't like the lava tube. If they're anything like lava tubes on Earth, and you've ever been to one, these are really rough places to be. They could tear your suit super easily. But on Earth, sometimes you get a side entrance. On the moon, we only see skylights where it's just a hole. And so you have a hole that you have to get down into. So I'm not totally sure how to get in there safely yet.
There's probably a lot of cavers out there that probably could make some suggestions about how to get in.
Oh, definitely.
So Christopher asks, why are there more Mare on the near side than on the far side?
Yeah, so on the near side, the crust of the moon is a lot thinner than on the far side. And there's a lot more radioactive elements on the near side. So what that means is the near side has a thinner crust and is hot. So with the thinner crust and a magma source underneath, volcanic eruptions were a lot easier. But on the far side of the moon, the crust was a lot thicker. So it was harder for the magma to seep through onto the surface on the far side.
Which I guess that would, the question that I would have, what came first, the thin crust in the Mare, or is the Mare because of the thin crust, or is the crust thinner because of the Mare? And so, kind of a chicken or egg sort of question. Maybe it's another open question. I don't know. So
yeah, I think it would definitely be something where the impacts happened and created the large impact basin, which created the thinner crust, which then allowed the magma from beneath to be exposed and to seep through cracks. But that's just a theory.
Yeah. We have to go and look.
Yes.
And maybe even drill to find out what's underneath there. That would be really great. So Kelly asks, why couldn't a rover or a robot get sent to determine the water before people go? So people going first.
Yeah, so we actually have the Viper mission, which is planned to go to the lunar South Pole. And what Viper is going to do, it's going to look at the surface of the moon and it's going to rove around and map out what it sees. It's going to look for water ice. It's going to look for carbon dioxide. It's going to look for sulfur ices. And then when it finds a spot that it thinks is potentially high in water deposits below the surface, it's going to drill down into the surface about 1 meter deep. And it's going to look at the different layers and see where the ice is and how much is present. So hopefully that'll be in, I believe, 2023.
All right. Okay, we're going to go for the last question here. And so this is kind of a double question. So Mustafa asks, how many Artemis missions are planned? And, and then he asks about the budgeting for these, about the allocation for budgeting for the various missions.
Yeah, so right now I am familiar with the 3 Artemis missions. So Artemis 1 to test the integrated Orion and Space Launch System. Artemis 2 will send astronauts to orbit the moon to fully test out all the systems with a human on board in the deep space environment. And then Artemis 3 is planned to send astronauts to the lunar orbit and then down to the surface of the moon. As for budgeting, our budget varies with the fiscal year budget through the government. And so the current administration is supporting Artemis, and so hopefully we will continue to have a budget to push forward.
Let's see. All right, well, thank you so much, Casey. This is absolutely fantastic. We had a lot of really great questions and a lot of really great information. So exciting to be going back to the moon. And it's really exciting to think about what we're going to do there and hopefully make it a place where people can stay for long duration. So thank you so much for joining us, and thank you everyone for tuning in. So everyone, you'll be able to find this webinar along with many others on the Night Sky Network website in the Outreach Resources section. Each webinar's page also features additional resources and activities. We will post tonight's presentation on the Night Sky Network YouTube channel. It should be there now since we are streaming. Also, join us for our next webinar on Tuesday, June 22nd, also with a little bit of a water theme. It's called Supersonic Snowballs in Hell, the Science of Sun-Grazing Comets with Dr. Carl Bottoms. So that'll be a good one. If nothing else, the title is definitely one to draw you in. So keep looking up, and we'll see you all next month. So good night, everyone.